Hello everyone and welcome to this module on Introduction to Continuum Mechanics. So basically in this module we are going to discuss the material volume and control volume in more depth, and we will present the Reynolds transport theorem, and we will use this theorem to derive the field equations once more, and we will solve some problems based on this methodology. All right, so let's get it started by the material volume and control volume. So in the last module of the fourth chapter, we already get to know the material volume and control volume. We said that control volume is something like a fixed kind of volume in the space that you select, and basically here you have some input from your, let's say, your surfaces and some output from the other surface, for example. And we have this volume control. However, the material volume is basically something that we select initially and we move with that. So basically it is like selecting like five molecules, like a gas molecule. So we select five gas molecules and we move with them. So it is constant. But for VC, for the volume control, this is not constant. At a time instance, it could be, for example, 3, another it could be 5, another time instance it could be 1. So basically, this is changing with time. So now we are going to further deep dive into these two terminologies to appreciate these better. So the book actually used a one-dimensional kind of problem. Uh, so let's suppose that x is the spatial coordinate. So we can use the capital X and T, and Y is capital Y, and Z is capital Z. And here we are going to use rho as the density to basically to discuss the change of mass over volume, a cylindrical volume that we have in here. So basically we have a cylindrical volume with this area of A, and its length is dx. So it starts from x1 and it goes to x2. And next we also, so this is VC. So we also have a VM, a material volume that I will explain next. So let's get started by the control volume VC. So let me just write down here that we are discussing control volume. So this is control volume. So you know that the mass is equal to rho times the volume. So if I want to write mass for the control volume, we'll have m, and we know that m is a function of x1 and x2 as well as the time. So at one time increment, it could be like some mass. At another time increment, it could be some other mass. So it is a function of x1 and x2, both small x1 and x2, because this is something fixed, arbitrary, completely arbitrary in the space. And t, so we have to integrate over this volume. So we have rho, sorry, as function of xt, and then we have dv. So instead of dv, we're going to write a, since this a is constant, and dx. So it is changing from x1 to x2. So now we are integrating over the control volume. So integral over control volume. So next we will have uh, like the same, let's say the same volume, but this time we have a material volume instead of a control volume. So a material volume. So now x1 and x2 are functions of capital X1 and x2. So let's say that we have x1, so it is changing from x1 to let's say x2. So I'm going to use these kind of notation to differentiate between, this material volume and this control volume. So this is in the reference configuration. So since this is in reference configuration, we have capital M. We use capital M, and we know that here M is a function of x1, x2, and we have we have time as well. So now we are going to know what is the mass of this material volume that we initially selected, as it coincides this control volume. So basically, we have an instance. Let me just take this a bit down. And just, I don't know if, yeah, great. I have it. Memory. So next, if let's say that this is VC, then we will have this dashed one as VM. Let me just change this color to red. Great. So now we have a time instance. So at an instance, when VM equals VC, we would like to calculate M, or the mass, which is of course M. So basically, this mass, as I already told you, at a time instance it could be 1, and another time instance could be 3, for example. But this one here, in the material volume, it is a fixed one. So we have, for example, 3 particles or 3 molecules in here, and we are only studying these 3 molecules. So at the time instance when Vm coincides Vc, so we know that x1, capital X1 and x2, they coincide with small x1 and x2. So therefore we can write this as rho x1, x and t, a dx. And now these these x1 and x2, since we already mentioned here that small x is a function of capital X and t, so they become a function of x1 and t and capital X2 and t. So that's why we write this capital M in here. So this mass, when the mass of the control volume, when it coincides with the the mass of the material volume, when it coincides with the control volume, we show it with M. And we also know that this mass in here is changing with time. As I already told you, at one time increment it is 1, again it is another time increment it is 3, another time increment it is 4, then it becomes 2, for example. So it is changing with time. So we can write the partial derivative of small m with respect to t is equal to the partial derivative. We write this integral again, x1 to x2 of rho x and t a dx. And this is when x1 and x2 are fixed in the space. We know that these are fixed in the space. So now, let's say that at the instance, so let me just write this in here also, that this is the rate of increase of m inside the fixed control volume. So this is the rate at which mass inside mass is increasing. Maybe it's better. Inside a fixed control volume. And then at the instance when Vm coincides with Vc, we are able to replace this m with this expression m in here. So partial derivative of capital M with respect to t is equal to, so we can write this expression in here, rho x and t a dx. This is x1 as a function of capital X1 and t. This is x2 as a function of x2 t. And this is where x1 and x2 are fixed. It's because, then x1, it coincides with x1, and x2, it coincides with x2. So at this moment, so we can replace this partial derivative with the material derivative, because it's like, x1, small x1 coincides with capital X1, small x2 coincides with capital X2. So it's like we are in the reference configuration. So we can take this partial derivative and just change this to the material derivative of x. So I'm gonna also remove this x in here because this is already what x is here, because x is a function of capital X1 and t. Small x1 is a function of capital X1 and t. So this x1 and t. Then we also have small x as a function of capital X2 and t, rho x and t a dx. Of course, when x1 and x2 are fixed. Let me just remove this in here. So we can write this as the material derivative. So the partial derivative is changing to material derivative. And this is basically, again, the rate at which mass is increasing when Vm coincides with Vc. This is very, very important. When Vm is equal to Vc. So here I have to also write down in here that this is the time when Vm is equal to Vc. So you have to be careful again here that this is the rate at which, sorry, the rate of increase of mass of that specific part, that specific part of material that coincides the fixed control volume at time t. So that's why you have to differentiate between Vm and Vc. So as I already told you, the mass inside Vm is constant because you select a certain volume of a specific part of the material. But in VC, we basically select an arbitrary kind of volume in this space. So mass is changing at one increment, time increment, it could be one, another time increment, it could be two, and so on and so forth. So if we are able to calculate this integral, so then things will get easier. And this is only for one scalar, let's say scalar uh, value in here, which is rho. But if we replace this rho with a tensor, then we can basically develop some other equations, and we can use these kind of, we can then derive the Reynolds transport theorem and use it to solve some problems. So basically, if we have Vc as the control volume, so if I, instead of rho, I write T of x and T dV, and this is over Vc. So if I apply this partial derivative operator in here, then it's going to be the partial derivative of T of x and T dV over Vc. But if I have the material volume and I have this tensor, arbitrary kind of tensor, x t dv over vm, and I apply this partial derivative, then I can change this partial derivative to the material derivative. So it becomes dt of t x and t dv over vm. All right, so now let's get to Reynolds transport theorem. So we're going to calculate this material derivative, because if we calculate this, we will be able to find how this parameter is changing with time. So let's say that you have the material volume of an arbitrary kind of tensor like t. This tensor could be density, as we already had in this example. It could be linear momentum, angular momentum, or whatever. and we are taking this over Vm, because Vm is because we are going to find this integral, the change of this integral when basically Vm coincides with Vc. It is at that time instance that we will be able to take this material derivative inside the integral. So d of dt, we're going to find this. So if I take this and if I put this in here, so this is equal to the partial derivative of t x and t dv over vc plus t v dot n ds over sc in here. And c, this is small v dot n. So here our basically our integral is changing from material volume to control volume and control surface, and this can also be written as partial derivative of t x and t with respect to t dv over vc plus the integral of t divergence of v dv over vc. And we will show this using if you remember, we had the material derivative of some function. It was equal to the partial derivative of that some tensor. So it was equal to the partial derivative of that tensor with respect to time plus its gradient times v. So we will use this and we will derive this equation as well. But let's just accept this for the moment. We will provide the solution. We will provide a proof in a minute. So this is the whole theorem. So just this. All right. So let's get us started here by the proof. So this is the first approach, proving the Reynolds transport theorem. So basically, we start from here. So we have d dt of the integral t of x and t dv over vm. And the book also used t in here to says that okay, this at the time increment t. So because this vm is changing with time. So because this is just moving. So we have, for example, as I already mentioned, 10 molecules, and this 10 molecules is moving up until it reaches and it coincides with the control volume. So that's why we put T in here. So this is equal to, so as I already mentioned, so when Vm is equal to Vc, we can take this material derivative inside the integral. So d dt of t dv, and I'm going to just remove just writing this x and t. So this becomes, so if I just do this, so it becomes vc. So we have the material derivative of t dv plus t, the material derivative of dv with respect to, yes, the material derivative of dv. So we already mentioned in chapter 3, module 2, that dv the material derivative of dv is basically equal to the divergence of v dv. So if we replace this into this, so then we have the integral of dt dv vc plus the integral of then we have t, so this is t and this is the divergence of v and this is dv. So this is velocity, remember, velocity gradient, and this is let's say v, it's volume. So if you write this as dt plus t divergence of v whole dv or vc, you're getting this equation in here. And so, yep, yes. So this is, sorry, this is dt. We are getting this equation in here. So we also need to get this equation. This was the material derivative, not the partial derivative. So next, and this is the global, the global equation. So you can use it for whatever coordinate system that you have. But let's say that for the Cartesian coordinate system, we have the material derivative of Tij dv vm t is equal to, then we have dTij dt plus, so this is a tensor, so we also expect to get a tensor in here. So Tij, so divergence of VV is a second order tensor, it's a vector, sorry, so it will decrease, let's say it's order by 1, so it becomes a scalar. Sorry, I said that this is this v is the deformation gradient, it is just the velocity. So I correct myself. And then we have the partial derivative of k with respect to xk. Then we get this as a scalar. So we have second order tensor plus second order tensor in here. So dv. So we're gonna use this equation here that I already mentioned. So the material derivative of tensor is equal to the partial derivative of that plus the gradient of that times v. So this is going to be, so this material derivative is going to be partial derivative of Tij with respect to t plus, then we have the gradient of t, which is going to be Tij with respect to because this is going to be a second order tensor, so this is xk, and then we have vk, so this will give us second order tensor, plus then we have Tij partial derivative of vk xk whole, let me just move this a bit, so this is going to be dv. So this is equal to, so this is like the integral, and this is over vc, of course. partial derivative of tij with respect to t plus, then this can be written as the partial derivative of tij vk with respect to xk and whole dv. So basically this can also be written as, so if I write this as this is, sorry, vc. So we have the partial derivative of tij with respect to t plus, so and this is dv, of course, plus, so this can be written as tij vk and k ds over sc. So this is equal to yes, this is equal to this expression here, or in tensorial notation I can write this dt integral of t dv over vm is equal to, so it is equal to the partial derivative of t with respect to t dv over vc plus the integral of t, and this v, k, and k, it's just the dot product of two vectors, so it is v dot n, and this is over sc ds. So this basically is what we have in here in the first line. Okay, so the next proof, the next approach for proving Reynolds transport theorem is basically using the reference and the form configuration. So basically, we start from the volume of the form configuration. So we have the Jacobian times dv0, where Jacobian was basically the determinant of f. It was the determinant of the formation gradient f dv0. So basically, if I write the integral of t dv over vm, I'm not going to write x and t in here. So this is basically equal to, so if I just if I have this equation here, so I times both by t, so then I have tj, or the determinant of f dv0, and I integrate over vm, and this is over v0. And if I apply, let's say, the material derivative in here, so I'm gonna have d over dt of t dv, and this is over vm. This is equal to the d of dt v0 t determinant of f dv0. And remember, since we are in the reference configuration, we are able to basically take this material derivative inside the integral. So this v0 d dt of t determinant of f dv0. So if I expand this, so it becomes v0 dt, the material derivative of t, then we have the determinant of f, plus, then we have t, the material derivative of the determinant of f dt dv0 whole. So we already had let's say, one important equation here, this one. So I'm gonna copy and paste this in here. And we also had another equation where we had dv was equal to the determinant of f dv0. It was in here where we started. So basically, we are going to find this, let's say, the determinant of the material derivative of the determinant of f. We're going to find this. So based on this, we have the determinant here. So if we take the derivative from here, we can get something out of it. So if I take the material derivative of this side of the equation, so I have the determinant of f dv0, sorry, dv0. So determinant of f dv0, this is equal to the material derivative of determinant of f dt dv0 plus determinant of f dv0 dt. This is 0 because we are in the reference configuration and this is not changing with time. So its material derivative is 0. So therefore we only have this in here. Therefore we have d of the determinant of f, material derivative, is equal to, so I take this to the other side, so it becomes dt of the determinant of f dv0, and this is basically nothing but dv, so this is equal to 1 over dv0 d dt. This is dv, and we know that dv dt, or the material derivative of dv, is the divergence of v dv. So it is equal to 1 over dv0, divergence of v dv, and dv itself is the determinant of f dv0. So 1 over dv0, divergence of v. Then we have the determinant of f dv0, where this cancels out with this one. So we have finally the divergence of v times the determinant of f. Great. So this expression is equal to this. So now, again, I can write this down here. So copy, paste this in here. So this is equal to the integral v0, the material derivative of t, determinant of f, plus t. Now we have, instead of this expression, we have this divergence of v, determinant of f, whole dv. So if I factor out determinant of f, so we have dt, the material derivative of t, plus t, divergence of v, determinant of f dv0, and this is nothing but dv. This is equal to d dt plus t, divergence of v dv over v 0, which is now basically our control volume, so vc. So basically this equation here is the same as this in here.